Hi, my name's Cameron Smith, and it's my pleasure to be presenting today my project for the 253 physics class. I wanted to use some of the skills that I learned in my physics class to address an environmentally themed engineering challenge, and I hope you enjoy following along with me as much as I enjoyed researching this project. So I'm going to start now. So today I'm going to be talking about building better wind turbines using the principles of physics. So why wind power? The question should be, why fossil fuels? Fossil fuel production and combustion is a major driver of climate change and releases pollutants that lead to death and sickness around the world, including in America. In the United States, 81% of our energy comes from oil, coal, and natural gas. And those are all fossil fuels and have all the negative ramifications of that. Um, Contrarily, wind turbines produce no greenhouse gas emissions during operation, and it takes just 3 to 6 months to produce the amount of energy that it takes to manufacture, install, operate, maintain, and decommission a wind turbine. Um, and they average about 80 times more energy produced than used in production. So they definitely do pay for themselves, and that includes their maintenance and scrapping at the end of the day. So wind energy is really interesting. It has the lowest life cycle emissions of all energy production technologies. So we can really get off fossil fuels, and that's why. And there are obviously wind farms that are located on land, and there are wind farms located offshore. Um, the principal advantage of offshore wind is that there's a lot more wind and it's more constant. Um, so these turbines here, they they're generating about enough power to um, keep 4,000 homes um, electrified. So they're really effective. Um, so you might have noticed that these things are quite huge. Um, as a 6'7" guy, I like to tell myself and most anybody who'll listen that bigger is better. And in the case of the wind turbine, physics supports this notion. So the power, um, theoretically, is equal to rho uh, times the area swept by the blades. So it's a bit bigger than that. This area times velocity cubed, and that's times like a constant for mechanical inefficiencies, which is known as the Betz limit. So you can see velocity and area are the drivers here. So the bigger they are, the better. Um, Now, being tall and big has advantages in power, but it has disadvantages. It creates more electricity, but there's also a lot more strain on the structure. Um, there's a longer moment arm here, and so the force at the head of the rotor here is really putting a lot of strain on the anchor, and that's a really interesting thing to look at as an engineer because um, what's happening in wind turbine design is really new and really exciting, and there's a lot to be done. So there's some really interesting problems here, and they have meaning. So the force that you see on average hitting the rotor amounts to about 2 meganewtons. that's 2 million newtons, so quite significant. That's a horizontal force. There's a vertical force here, just from the weight of the structure of, roughly 8 meganewtons. And then there's, sometimes these huge waves that can hit the kind of pylon that are in the area of 5 meganewtons. And then there's again all this moment here. So you have there about 20 to 50 meters of pylon or structure that's underneath the water. That's at average depth, and then at about 90 to 100, that's above. So there are three components to designing the foundation here, which keeps it all hunky-dory. And those three things are basically the soil that can change from spot to spot, the design of the anchor. There's a number of different, very, very varied designs for anchors, and there's not so much agreement about which ones are better. And then, of course, the load that the structure puts on the anchor is also key. So how does one go about designing a foundation? How does one keep this wind turbine from falling over? That's a really good question. So here are some examples of wind turbine anchors. We have a floating wind turbine, which has two suction anchors here. We have a monopole anchor, and we have various other things. But the the thing is, the computer models are quite rudimentary and kind of just kind of estimates at best. So that's where doing experimentation to validate the models and algorithms and whatnot is pretty key. So this is kind of what I have been planning to do, which is to use the UCSD centrifuge in the Jacobs School of Engineering there, and actually do some testing. I've got a connection there, so this was going to happen before Corona kind of put a temporary freeze on things. So my plan was to actually test scale models of different foundations in soil, which goes in this bucket here. And the cool thing about centrifuges in geotechnics and structural engineering is that if you spin this guy around fast enough, this centrifuge here, this rotates, it'll actually generate enough centripetal force inside this bucket that it'll start the bucket contents. If it's filled with soil and some kind of miniaturized anchor, will start acting like a anchor that's many times larger at the bottom of the ocean and has several tons of weight above it. So that gives us an opportunity to have a really cool simulation, and there is also the potential to have an actuator here, which is cyclically loading the anchor. And of course, you would be remiss not to have some kind of sensor here. So the sensor is going to be really important because it can basically show you where your design is wrong when it comes to making an anchor or looking at some kind of soil movement. So what kind of sensor would be ideal. And that's where the optics comes in. And that's where got really exciting for me because I discovered a new kind of sensor in my research based on basically fiber optics um, and kind of refraction. And these sensors are used in robots, and they're used in structural engineering to see if bridges are moving or cracking or whatever. And they've been around for 20 years, and they're named fiber Bragg grading sensors. And if you guys don't recall, the physics of fiber optics is pretty interesting. Um, Basically, the index of refraction is such that the light actually it has a total internal reflection inside this uh, kind of light tube of silica. Um, and so light kind of flows like sort of like electricity through fiber optics. So they're used in cables and in sensors and all kinds of cool stuff. So I'm going to show you now what's happening with a FBG sensor, fiber Bragg grading sensor. So a full spectrum of light is shone down a fiber optic cable, and it's there's a wave like this corresponding to the basically this wavelength of light, and that is reflected back. And depending on these gratings, a different wavelength will be reflected. And what happens is when this section is stretched or compressed, this reflected light signature actually changes in wavelength there. So pretty cool stuff. And that is really another really cool thing is you could have up to 20 of these gratings of different dimensions along a fiber optic cable, and they could be detected by the same detector that detects the reflected light, and all be simultaneously sensing strain. So they're super neat, and I'm really excited to use them. So I have, in my kind of traditional, scientific way, come up with some hypotheses. The first of which is that the failure of foundation anchors are sudden, following normal behavior during cyclic load testing. The second is that the helical anchor failures will present with some kind of disturbance, basically in the soil, proceeding very soon before the anchors pull out. Third, that the FBG sensors can show a 3D model of the soil movement before and during the anchor failure. And four is that different types of seafloor soil will have different kinds of behaviors. So now the really interesting part, and I think one of the most challenging parts, is how to make a 3D picture of what's happening when this anchor is being pulled out after being cyclically loaded. And that's something that I think I was looking forward to doing a kind of iterative testing. But I think having some kind of like grid of the FBGs would be the go and totally feasible. They cost about $120, for a 20 20 sensor line of fiber optic sensors. So it's totally feasible, and I don't think it has been done before. So I think it'd be very interesting for people who are designing um, wind turbine foundations. Um, so right now, this is on hold, but I've learned a lot, and when things open up again, I'd like to pursue doing this testing, and that's that's my research. So I thank you for watching, and I hope you I hope to enjoy watching some of the other presentations. Okay.